Hello everyone, my name is Chejin Lim. Today I am here to introduce my research area and my recent paper. The paper is titled AdFlush, a real-world deployable machine learning solution for effective advertisement and web tracker prevention. When looking at a research paper, I prefer you to think about what the title means and what kind of story the author is trying to tell. In this paper, we can focus on why should we prevent advertisement and web trackers, and what are web trackers in the first place? Then, why should we use machine learning to solve this problem? And at last, we can try to find out how this was implemented to make a real-world deployable solution. Before talking about the paper, I'd like to introduce our lab, the security lab. We are supervised by our best professor, Hyung-sik Kim. In our lab, several research topics are covered, including traditional security, such as Androids, authentication, phishing, and so on. We also have high interest in machine learning security, incorporating both security of MLs and using MLs in security. Professor Hyung-sik Kim is also a very famous icon in usable security, and this is about how human factors impact the role of security measures. Our lab is great in publications, as we have 3 successful publications only in this year out of the Big 4 conferences in security, and many much more. We think that the best research is done with a shovel, not tweezers. This means what you've made could actually change the world into a safer one. This paper was published in WWW 2024. The WWW conference is the WWW that we all know, the World Wide Web. And the conference is very famous in data mining, information systems, and all sorts of topics related to the web. Even though it is treated as a second-tier conference in security, the acceptance rate is not that high, only about 20%. Let's move on to the paper now. Web advertisements. We all know about web ads. These services are useful in the aspects of marketing, but as us users, they are quite annoying and even sometimes intrusive. Is that it? Well, no, it's not. Advertisements introduce several threats, such as malvertising, which introduce malware to the victim's local device. Web trackers, heavily related to ads, are web applications that collect user behavior and send them to the ad services. Originally meant for targeted advertising, web trackers also introduce threats such as user profiling and thereby hindering user privacy and security. So, ads and web trackers bring risks to user privacy and security. So what should we do about these ads and web trackers? One popular way is to use ad blockers. Filterless-based ad blockers are lightweight, easy to use web browser extensions, and some of you might have used one of these. However, relying on manually created blacklists, these filterless ad blockers require intense human resource and frequent updates. Also, these blacklists are actually strings of the destination URLs, and they are vulnerable to evasion because as these lists are open sourced, the attacker can change his ad's URL, and changing a URL is an easy thing to the ad authors. This is why researchers these days are moving on to use machine learning in preventing ad and web trackers. They are well known for their great generalization performance that could reduce the human labor and achieve good results. However, the recent and best so-called state-of-the-art models or SOTA models all suffer in having heavy runtime overheads. We collected 3 SOTA models, AdGraph, WebGraph, and WTA graph, the top 3 models that were recently published in the Big Four conferences in security. When covering baselines or comparisons, it is always a good practice to aim high and try to compete against great papers. We used our test data set consisting of 166,000 HTTP requests. AdGraph and WebGraph consumed over 17 seconds to inference the whole test dataset, and WTA graph required over 140 seconds in inference. We can think that AdGraph and WebGraph doesn't take that long, but it is only an inference. And in the real world, there are many situations that feature extraction takes much more times longer than inference. This makes the models too slow for real-time prevention because the user must wait for the model to let him or her send the request or not. We can also see that the models consume too much CPU and memory to prevent ads and web trackers on the user's local device. Well, who wants to use up to 1.3 gigabytes to run an ad blocker? Also, we found out that these existing models require features or machine learning input values that are only obtainable after the request reaches the ad server. Extracting these features means that the user's privacy is already delivered to the ad authors, and it is no use to prevent them after this happens. For example, a feature name outDegree is the feature that indicates the number of communications that a web component successfully sent. During this delivery, the user's sensitive information, such as UUID or user's universally unique identifier, IP addresses, or device IDs, are also sent to the server. When these infeasible features are all prepared, and at last the model predicts whether the request before was an ad or tracker, it is already late. Also, are the machine learning based ad blockers robust? And this means that do they withstand against evasion attacks? The bad news is no. We showed through our experiments that these 3 models suffer in several adversarial attacks. Well, in precise, we discarded WTA graph due to the low performance in the first place. AdGraph mainly uses URL features. Thus, upon URL manipulation techniques, the ads and web trackers were able to successfully attack and deceive the model by over a 10% ratio. WebGraph uses complex features, such as features from JavaScript source codes and graphical features. Thus, we performed actual JavaScript specific attacks and general attacks such as using GANs and achieved an attack success rate of 14 and 11%. I will briefly explain about the types of features later. So this gives us a brief view about what we should do now. We have to make a new solution that is lightweight, using only practical features that is obtainable before the request fulfills. A model that achieves high performance and is also robust to evasion attacks. We specified these goals into stepping stones to build our solution, AdFlush, that can flush away all your everyday ads and web trackers. Let's first look how the data samples containing ads and web trackers look like. Actually, they are HTTP requests consisting of HTTP headers, URLs, JavaScript for source code or website requests, and graphical features. An example of a HTTP header is on the left, having several values related to the request. An example of graphical features is on the right. Graphical features are calculated from building a graph of the components and the communication between the components of the web, as in the example below. To move on to construct AdFlush, we first included robust features. The first type are URL encodings. These encodings transform URL strings into vectors that preserve the meanings or characteristics of the original string. This vector is hard to change by simply perturbing the raw URL, thus robust to URL perturbing evasion attacks. We trained a character-to-vector model to encode these URLs. The second type of robust features are JavaScript features. What kind of behavior a website does, or how the source code is written, is transparent to the user due to the open-sourced manner of the web. Everybody can open their web browser and press F12 to see the source code of the website you are looking at. Therefore, the authors of the source code try to hide valuable information or critical functions by messing up the source code as below, called obfuscation. This makes it hard to analyze the behavior of these gibberish source codes. Therefore, we could build abstract syntax trees that represent high levels of the behavior a source code does, which preserves even after obfuscation. Have you ever heard of tree traversal algorithms? By reading the abstract syntax tree in pre-order with a window size of n, which is 3 in our case, we can collect patterns that represent the source code's behavior. The first pattern would be minus operator, function call, and variable. The next existing pattern would be function call, variable, and the value f in this example. These are called n-grams. We calculate the frequencies of all existing n-gram patterns within a source code to figure out what the patterns the source code uses. These patterns preserve during obfuscation because obfuscation only tries to change the presentation of the code, not the actual behavior. This means that by using this feature, even through obfuscation, we could decide whether a source code is including as or not. We also included several statistical characteristics commonly seen in obfuscated code. For example, obfuscated source codes commonly result in one line of code that is enormously long. This makes our one of our features, character per line, a very high value, distinguishing source codes that are obfuscated. With the features that were used in existing methods, combined with our robust features that we included, we came up with a total of over 3,800 features. In order to make our model lightweight, we decided to reduce the number of features and leave only the essential ones. We therefore conducted a thorough feature engineering process consisting of 4 steps. We removed infeasible features as described before that are only obtainable after delivery. We identified the infeasible features by manually observing the source code of the data in our dataset. Then we removed insignificant features that act as noise by having statistically low relationship to correct answers using point biserial correlation coefficients. We also removed less influential features by recursively training 50 simple models with different sets of features. If the performance of different feature sets do not differ a lot, the difference between the set of features has less influence upon the model. Then it is free to eliminate the difference of the feature sets. This process is called recursive feature elimination with cross-validation, or shortly, RFECV. Finally, we removed redundant features using Pearson and Spearman correlation coefficients. These values represent the statistical relationship between two features. If one relationship is significant, then the two features represent similar knowledge. If leaving these redundant features in the input, the model might overfit on the features that have been looked over multiple times more than other features. Therefore, as a result of this process, our final set contains only 27 features, a very compact yet effective for preventing ads and web trackers. To select and train our machine learning model, we used a library called H2O AutoML. This library automatically selects the model architecture and hyperparameters that best perform on the training dataset. When using datasets that are in tabular form, such as our dataset, it is handy to use such libraries, and this helps you obtain the best performance. Our process resulted in a gradient boosting machine. Our test performance achieved the highest performance compared to the existing models, even with the fewest features. To give a brief explanation of the performance metrics, first of all, accuracy is the percentage of the right answers. Precision focuses on the percentage of the true level data that the model classified right. This means a high precision indicates that when a model predicts that a sample is an ad or checker, it has high chance that the prediction is right. Recall is the opposite of precision. If a model has high recall, then the model has high chance to catch all the ads and web tracker within the dataset without missing some samples. Focusing on only one of the precision or recall is not a good practice. Let's say that a model always answers that a sample is an ad or checker. It won't miss any ads or checkers, achieving 1.0 recall, but will have a terrible precision, and no one would use that model. To balance between these two metrics, F1 score is the harmonic mean of precision and recall, commonly used to show overall performance even in imbalanced datasets. In the field of advertisements and web trackers, I prefer to achieve high precision because missing one ad doesn't harm the user that much. But making a wrong answer and blocking a normal request might break up the entire website. Then, the angry user might not use the solution at all. We further performed experiments to prove the robustness and efficiency of AdFlush. Upon several adversarial attacks, AdFlush only allowed at a ratio of 2 to 5%, allowed attacks at a ratio of 2 to 5%, significantly lower than the existing SOTA models. We also consume the least amount of CPU and memory usage in the shortest amount of time to prevent ads and web trackers. In order to prove that our solution is deployable and usable in the real-world web ecosystem, we implemented our model into an entire web browser extension framework. This browser extension contains our pre-trained model and goes on the user's local web browser. When an HTTP request initiates, AdFlush directly extracts the 27 features from the HTTP request and feeds it into the machine learning model. If the model predicts that the HTTP request is an ad or a web tracker, then the web browser extension blocks the HTTP request and saves the day. A running demo of AdFlush is on YouTube, and you can find it easily by searching AdFlush. The left browser is one that has AdFlush installed, and the browser in the middle is the one without any ad blockers. The right panel is for debugging and logging. You can see that the ad banners are completely blocked by AdFlush, and that your privacy and security is safeguarded against the ad servers. So it's it. Feel free to contact me. Here is my email, and here is our lab's website. I am willing to answer any questions about my paper, cybersecurity, or life as a graduate student in SKKU. Thank you for listening, and have a nice day.